So please join me in welcoming Dr. Yifan Yu.
Yeah, thanks for the introduction. Today I will be talking about the image-based meta-analysis from the aspect of method and algorithms. So far we have learned about the procedure of doing image-based meta-analysis, or IBMA. And now I will give a very quick overview about each steps of running IBMA. So firstly, we have the subject level. For each subject, we have the pre-processed data. And so firstly, we run first level model fitting and estimation on the pre-processed data for each subject. And that will give us the subject-specific contrast and standard error maps. And then in the study level, we combine these subject effect maps by running the second level model fitting and estimation. And that will give us the contrast and standard error maps at the study level. While finally, at the meta-analysis level, we put all of these study-wise maps by running the third level model fitting and estimation. And that will give us the final overall contrast and standard error maps, followed by the inference to identify the robust activations. And the main purpose of IBMA is to combine study-level statistical maps to identify patterns of activations. So as you have already know, the coordinate-based meta-analysis is limited to thresholded peak coordinates, while image-based meta-analysis uses unthresholded statistical maps, for example, the effect size map and the variance or standard error maps. Therefore, IBMA produces more accurate and detailed results. The key output of IBMA is, so firstly, combined effect size map and combined standard error maps, as we have noticed from the previous figure, as well as the significance map, for example, Z-maps, as well as the between study variance measures, so I-square or tau square. As for the key inputs for IBMA, so firstly, effect size maps represent the voxel-wise beta values. It is a fundamental spatial effect estimate for IBMA. And then T-maps represent the unthresholded voxel-wise T statistical maps. When we know the sample size, we can easily convert it to standardized effect size into like beta value or Z value. Similarly, we have the Z maps, which represent the unthresholded voxel-wise Z statistical maps. It's also it's already standardized, and when we know the variance, we can easily convert it to beta values. Additionally, we also have the variance map, which represents the voxel-wise variance or standard error of the effect. And it is useful if we want to weigh the study inversely by uncertainty. And sample size is also another key input for IBMA. It represents the number of participants, and when the variance or standard error maps are unavailable, we can use the sample size to approximate weight. So after knowing the key inputs for IBMA, the next question is how do we run IBMA with these inputs? So the first column represents the input that we have just talked about, like standard error, contrast estimates, T-maps, Z-maps, p-value maps, and sample size. If we look at the column in the middle, so these are the IBMA methods which have been implemented in Nightmare. And we notice that each method dependent on different inputs. For example, most of the methods rely on standard error map and effect size map, while some of the methods, like for example, for fixed effect hedges, we only need the T-maps and sample size. And for Stauffer and Fisher's method, they rely on the Z-map. And all of this method can be categorized into like fixed effect model and random effects models. And I will talk about like the definition for these two different model types. Firstly, fixed effect IBMA and random effects IBMA are different in terms of the assumption of underlying effects. So the fixed effect IBMA assume a single true effect mu across all studies, while IBMA assumes study-specific true effects, which are drawn from the distribution with mean mu and between study variance tau square. They also differ in the assumption of observed variation. So fixed effect assumes it considers only the within study variance, while random effect considers both the study within study variance and the between study variance. The fixed effects is limited to the included studies only, while the random effect can be extended to future or different studies or different experiment conditions. And their practical implications are also different. So the fixed effect might have higher rates of type 1 error if we ignore the heterogeneity across studies, while random effects IBMA are preferred if heterogeneity between studies is anticipated. So now I will dive into more detail of random effects IBMA method. So that, as we have mentioned, so it is random effects generalized beyond the studies that we have collected. So if we have look at the figure on the right, there is distribution for each study's estimated effect, which is represented by the little black curves. We notice that these distributions have different mean, which represent the across study heterogeneity. And we compare the random effect significance against the population mean, which is the mean for the distribution underneath, like the wider distribution. And we compare the population mean against two sources of noise, which is either within study variation for each small distribution, and it is denoted as sigma fixed effect square here, as well as the between study variation, which is denoted as sigma random effects square here. And if we only use fixed effect model, we don't consider the between study variation sigma random effect square. So we are only so we can kind of imagine it as all of the small black curves for each study have the same mean, but so in this case we only consider the within study variation for each of them. And I will talk about one method specifically. So it is Stauffer's method when suppose all a study gave us is unthresholded Z-map. So the standard Stauffer's method is given by the first expression. So it's simply by averaging all the Z values across each study I. So it is a fixed effect model, and each study contributes equally, and we also assume that each study has the same precession, while in reality it might not be the case. So that's why we consider the sample size weighting. If we have look at the second expression, we assign the weight of square root of Ni for study I, which is the square root of sample size. So for larger Ni, it represents higher precession, so that's why we assign it with larger weight. So for example, if we have study A with 16 participants and study B with 16 participants, if we take the square root of 64 and 16, we realize that we assign twice of the weight to study A than study B. And the denominator, the square root of the sum of ni, is used to rescale the whole expression to standard normal. And now I will talk about 7 frequently asked questions when running IBMA, which is like sadly sometimes the reality when we run IBMA. So the first classical scenario is we have mismatch contrast. For example, one contrast is against a baseline and the other one is against another condition. It is bad for IBMA because IBMA assumes a single shared effect definition across all studies. And if we mix like condition versus baseline with condition A versus condition B, it will give us incomparable effects, and the pooled effects become unreliable. So in this case, we should either like harmonize the contrast. So if we have the first level data, we can recompute all the study to a common baseline, or we inverse sign for consistency, or with stratified analysis. For example, we can run separate meta-analyses for each contrast type, and then we compare the patterns. Or we can simply exclude the mismatch contrast. So here is an example for the mismatch contrast. So the figure on the left is 2 back versus 0 back, while the figure on the right is 2 back versus fixation. And we notice that there is a huge difference if we look at the activation regions. And that will give us very like inconsistent result if we ignore their mismatch contrast. So the second scenario is when we have very limited number of studies. For example, we only have 4 to 6 studies. In this case, the degree of freedom can be very tiny, and we have very heavy tail for T or Z. And the tau square, like the between study variance estimates, can be very unstable. So in this case, we should switch to fixed effect IBMA, or we should broaden our inclusion criteria to add more studies to increase like more powers. So the next scenario is when we have missing variance map in IBMA, because most of the IBMA need both beta and standard error maps for the inverse variance weighting. As we have, I have mentioned, each study's contribution is proportional to its precession, and it's defined as 1 over variance. So, for the studies without standard error, it cannot be weighted, and if we just mix them, it can like bias the result. And if we just drop these studies, it can cut down the effective sample size in half. So in this case, what we can do is, firstly, we can run separate analysis. We can run the full model, which includes both beta and standard error for studies with incomplete inputs, with complete inputs, and we can run partial models, which has T-maps and degree of freedom or sample size n for the rest, and we compare the spatial pattern for the robustness. Or we can approximate standard error from the available T-maps and degree of freedom when possible. Or we can just request more data by contacting authors or repositories to obtain the missing variance maps. Another scenario is we might have inconsistent pre-processing across the studies, which is actually quite common. So different papers, different publications might use different MNI template, different voxel size or smoothing kernels, and that will misalign the peaks. However, if we just simply average the misaligned data, it will blur the true effect, and it will inflate the variance non-uniformly across the brain. So in this case, we should, firstly, we standardize the space. We resample every map to a single MNI template, and then we can match the resolution and smoothing by mapping them to the common voxel size, or we just add or remove smoothing to achieve similar FWHM across studies. And we should also apply the common mask. We can also run sensitivity analysis by rerunning IBMA with or without studies that deviate most in the pre-processing to assess robustness. And the next scenario is we might have very tiny individual sample size. For example, we have less than 10 studies when we want to run IBMA. And with very limited number of studies, it can give rise to very large standard error. So the effect estimates are very unstable. And excluding many such studies can inflate between study variance, and it can affect the reliable signals. So in this case, we should do firstly sample size correction by applying Hedges G or similar method to reduce positive bias in effect sizes. And we can also do robust weighting by down-weighting the studies with extreme standard error. And we can run sensitivity analysis to exclude the smallest N studies to understand their impact. And the next scenarios is we might have thresholded first level maps. It is bad for IBMA because zeroed voxels or outside of clusters can break the normal noise assumption. And that will make meta-analytic Z-maps show blocky rectangular cluster or unexpected holes. And in this case, we should either request raw or like unthresholded maps from the author, or we take one step back to CBMA for studies without thresholded images. And we can also do sensitivity analysis in this scenario by rerunning IBMA to exclude thresholded images. And the final scenario is we might have overlapping subjects across studies, because in reality, different publications might have shared participants, and it violates the independence assumption. And if we have the duplicate data, it will shrink standard error and tau square and inflate the significance, and it will give rise to higher false positive risk. So in this case, we should detect overlaps by cross-checking project ID or scanner site information, also lists, correction periods or Kahoot names, and we deduplicate by keeping one map per subject's Kahoot or averaging duplicates before meta-analysis. We can also do robust modeling. So if the overlaps remain uncertain, if the overlap information is missing, we can use cluster robust variance estimation or multi-level IBMA that models correlated studies. And now we have no many IBMA method, and this is a flowchart or a decision tree for making decisions on how to choose the best IBMA method for our data set. So the first question we should ask ourselves is, so are we exploring consistent patterns associated with occurrence of certain words or concepts? If the answer is yes, we can move to neuroscience. And we can also look into, so are the maps with standardized effect size available for all studies? If yes, we can move to weighted average of effect sizes. And we can also look into are the contrast estimates available for all the studies, and are the standard error maps available? If the answers are both yes, we can do third level GLM. And are the Z maps available? And are the sample size known? So if the answer is yes, we can do Stauffer's average of if the sample size is unknown, we can use Fisher's sum of P. And if we have the P maps available for all studies, we can check if the sample size is known. If yes, we do Stouffer's average of Z, otherwise we do Fisher's method. And then we check if some studies images are available, and are these maps like T maps, or can be converted to Z maps. If the answer is no, we use parametric voxel-based meta-analysis. If yes, we use like SDM. And the final step is, are the coordinates of local maximum available? And we also want to ask ourselves, are the coordinates accompanied by corresponding test statistics? If the answer is yes, we move to parametric voxel-based meta-analysis. If the answer is no, we use like CBMA method like ALE or MKDA. And I will quickly talk about an example of running IBMA executive function network labels. So for this data set, we have 69 papers included, and we have 158 SPMS. And we classify the executive function networks labels to the 9 frequently used labels of topographically or functionally similar networks. So the first IBMA we run is we investigate the consistency within and across labels. And for each network labels, we average the variance normalized SPMs, and we calculate the Pearson correlation coefficient between each label-specific mean maps and the overall executive control maps. And we consider the spatial correspondence to be strong if the Pearsons are exceeded 0.6. For the second IBMA, we investigate the spatial topography of the distinct networks, and we run the permutation-based image like IBMA on this data set. So for each cluster, we renormalize the maps, and we analyze using NIMIR by a permutation one sample t-test. And at each, so specifically at each iteration, we randomly flip the voxel sign to build a voxel-wise null distribution. And then we compute the t values by compare with these null distributions. And this figure shows, so the figure A on the left is the result of spatial consistency among SPMS, and it investigates both the Pearson's correlation coefficient between any two SPMs labeled within the same networks, as well as the Pearson's correlation between the average of all SPMS for given network labels. And the figure B on the right is shows the similarity between the 9 networks labels of interest. So that's the end of my presentation, and thank you for listening. Thank you for your time.